Multiple copies of this data are available in different caches around your system. And now you have two problems. One is, when you read that location, you have to be sure that that one is the latest version of the location, because some other people working on that location might have changed it before you read it. The second issue is that you want to write to that location and you change it. If you change it, your peers are in the similar position. You change it and they should be aware of that. And this kind of story, you know, you can see in this this simple diagram. This is called cache coherence problem. And you see you have two CPUs which are accessing the same address, which is cached within the two CPUs, and you have the value in the memory. Then, first time you read on A, you get in the cache a 1. You read on B, you get in cache in B a 1, and then you write a 0 on A, and then you have an incoherent situation. You see, you kind of did something already, right? Because also the value in the main memory is changed. What kind of cache do I have in processor A? Come on. You should help me. Otherwise, I go home and hang myself. Come on. What type of cache?
One-way cache? Two-way?
Two-way cache?
Two-way
10-way cache? Come on. Oh my God. Then I will cry in the afternoon. What type of cache do I have on processor A if when I'm writing in cache, I also write in the main memory? Write through.
Yeah,
Why was that difficult to answer? If I would not have had a write through, only column with cache value, third column would have changed. Yeah, this is kind of, you know, how should I say it in a nicer way? I better not say it. That's the best way to say it, just not saying it. But the fact that I mentioned it, it's already bad, right? You should feel like not comfortable about that. If I would not have had a write through, then I would have had 0, 1, 1. Now, the fact that I made that kind of write to the cache may help me or not. But still, CPU B should be aware of the fact that I changed the value. Because if I'm not telling CPU B in any way that this happened, next time when CPU B will need the value of X, we'll take the 1 instead of 0. And in order to deal with this phenomenon, there are a number of problems. And essentially, there are two types of problems which are coming from this memory structure. One is called coherence, and the other one is consistency. We'll be speaking about those in the next, I don't know, half an hour, 40 minutes. But essentially, the cache coherence relates to the fact that when I look for a location, I always get the right value for that variable. Then I will take care that when some of the users of that variable is changing it, all the others are aware. If I'm not doing that, then I don't have coherence. Then a variable may be alive in the system with different values. Now, the consistency relates to the behavior of other location and relates to the order, if you want, of the accesses. And from the coherence, I am getting, from the consistency, sorry, I'm getting that problem with the behavior, which might be different. when I'm issuing read and writes, I have to be careful about the order. If the order is correct, I'm preserving the sequential execution. Then I have a very consistent system. But the price for that is huge, and it's actually killing most of the performance improvement. And for that, we allow for some exceptions. Now, you see here you have two processes, and those codes are running in parallel. Now, you start with the initial value for A and flag 0, and you execute. Can you tell me for sure what will happen with process 2? Will I print A? What is the value of A?
Yeah.
Can you tell me that all the time?
No.
Not really, because you don't really know how the completion of the things are. You know, if I'm doing the while flag is 0, before the assignation of A is 1, I may get inside and I may write a 1 or a 0, depending on what's happening there. The order of those writes. Then I assign A a 1, and I have flag 0. If the synchronization is very nice, I will get inside the loop. And now depend if, assuming that the first instructions was executed in parallel, you might expect that I will print a 1. But you don't know that because, you know, this happened in a processor which is miles away from me. I may or may not see the consequences of that assignation. Then I may get inside the loop and I may print a 0. Then I will loop again because I will not see the consequences of flag being 1, and then I will write a 1 in the second iteration. This will depend very much on how the system will react. This is something which you didn't see in sequential programs, right? And the intuition, you know, it's what you said, right? It will happen in a nice, you know, the flow will be laminar and will go very nice like that, but that's, it may or may not be the case. Okay. Now, there are a couple of issues related to the coherence, and those are the conditions. And the first story is that if you write in the same processor and no other writes are done by other processor to the location, the value that you will be reading next should be the one that you wrote. If there is interaction, then the interaction may create some problems, and if between two writes in different processors you have enough time, you have a coherent memory because you will see all the updates. If there is not enough time between them, some of the processors may not see all the updates. Then I am writing a value on a location, you are writing a value on a location, and other people which are still looking at the location may or may not see all of them. And that's, you know, that will have an influence on the execution. And the other one, it relates to the write serialization. Then what you are trying to do, you are trying to follow the principle of serial execution, and you are doing the writes in the order which is imposed by the application. Now, this means that somehow you will read the values in the proper way. Now, in order to do that, you have to pay a price. And this is one of the big problems in those kind of systems. Now, and to enable coherence, there are two strategies. One is called snooping, and the other one is directory based. Now, snooping means that you have the normal traffic on the bus or on the network, but it will be easier to explain you on a bus, which will relate to data transfer. But you will have also an extra traffic which will relate to the synchronization between copies in different locations. Then whenever I'm writing to my local copy, and I will invalidate the value of that location, the other processors should also be aware of that. And now I can do that in different ways. And one way will be to say, I changed that value, then I send the address that I changed, and I send is not valid any longer. Which means that all the other participants should listen to the bus and see, okay, I have an address which I also have in my cache. Then I make a tag comparison, and I see, I have it too. It's not valid any longer. I'll invalidate it. Or I may even send the value, and I say, okay, this is the address, is not valid, this is the value that you should update. If I go with a write-through cache, I better not send the value, because the value will be in the main memory, and the others will take it from the main memory whenever they need it. Because, I'm changing the value, and only one of the other processor will eventually work on it. The others don't, then they may not need it. Those are kind of implementation details, and depending on how your cache is organized, you go for one or the other. If you don't have a write-through cache, you have to broadcast also the value. And now, this is nice in principle, it's kind of elegant, but creates a lot of traffic on the bus. Because you have, what you actually would like to do is to have the normal communication traffic for exchanging, writing data, things like that, and do that synchronization without having any pain or suffering on the application. Then you should make a wider bus, but this will cost you more. Okay? And you may get to situations where the bus traffic is actually increased in an artificial way due to that kind of synchronizations. Now, in each cache location, you have to keep track whether or not that location is shared or not. If it is not shared, it's yours, you don't have to do anything. If it is shared, you have to do things in a proper way. Now, there is another one which is called directory based. Then instead of having that kind of structure, which is distributed, then nobody has the overall situation of the system, which is in snooping. You can have a directory somewhere, and that one is in charge with the actualization of the things. Then whenever you want to know about a location, you ask the directory, is that shared or not? And the directory will do the job for you. Now, again, both of them have pluses and minuses, and depending on how many processors you have in the system, you may go for one or the other. Actually, this director-based, it's older than the snooping. And the snooping was kind of invented. Okay. Now, in snooping, there are two flavors. One is called write invalidate, and there is another one with update too. And in here you have an example on what's going on, and let me, okay. Then essentially here I have the same situation, but now I don't have a write-through cache, and processor A, which is making the change to location X, it's only changing the local copy, and it's sending to the others the fact that that location was changed. No value, nothing. When CPU B would like to use that data, we look in the cache and we'll see, this is not any longer valid. Then I have to solve this problem. And then in order to solve this problem, it will be a cache miss, which will update the CPU B and will update also the local memory. Then in this way, I'm not sending the information to guys which are potentially not wanting the information. This one is somehow different in the sense that in here, when I do the write, I'm doing the broadcast. Then the next guy, when he's looking for the value, will not experience a cache miss. The value is there. Now, which one do you like more? One, you have to have a choice. You know, some people like beer, other people like wine. Dutch people do mostly like beer. Dutch beer. Heineken. No? Why not? Not good Heineken?
It's awful.
I share that opinion. But, you know. Yes?
When you broadcast it, you don't have a cache miss, so maybe that's better.
Yes. That's one opinion.
I think the first one is actually more efficient because it doesn't take time on the other CPUs. Maybe they don't need the value in X at that time.
The CPU actually is not doing anything. It's the cache manager controller which is doing that. Then at the end of the day, what you have to look at is the traffic on the bus. Which one is generating more traffic? And you see here you have an analysis of what is one and what is the other. And you see there are some kind of things. And at the end of the day, if you draw the line and you calculate, write invalidate is better because the bus traffic, bus bandwidth is very important for the application to run. If you do the second one, which I agree with you, it's more elegant, you know, from the point of view of the elegance of the solution, the second one is more elegant. But if you do that, you generate traffic on the bus. Because the invalidation, you can do it also on a separate kind of channel without loading the bus. And for that reason, you know, write invalidate, it's just, you know, better. Even though there are consequences, as you said, in a miss. Then I know it's not good, it's not there, then I have to bring it from the main memory. Okay. Then again, we look a bit on the same story, and we hear, depending on the decision on other things in the system, one solution or another may be good. Now, if for some reasons you want to use write-through caches, it's better to go one way. If you have write-back caches, maybe it's better to use Snooping. Now, one of the issues in computer architecture is that decisions cannot be done on local things. And sometimes some of the parameters of the design are not in your power. They might be determined by other kind of conditions. And as you will see also in the lab, what you do, it's a design exploration. You are trying to look for different kind of solutions, not exactly in a mathematical driven way to find the best compromise. You are a bit like walking on that curve for looking for the minimum minimorum. You don't want to get to the minimum minimorum. You just want to find a solution which fulfills the boundary conditions which the, let's say, the marketing guy gave you. And those are acceptable energy consumption, acceptable price. And as an engineer, you will have to face issues which you most likely hate, because otherwise you would have gone to economical studies. Unfortunately, life is not like that. The guy from the marketing is actually paying your salary. Like it or not, that's the way things are. They are also paid better because they bring the money. Today it's kind of weird. We all know how to do things. Some know how to fabricate them, but the most important part is to sell them, which is not simple. Huh? I should not have said that in an engineering school. No, but it's good to be aware about the reality, right? Now, okay, those are some of these. I think I can skip those. Then, those are essentially details about different kind of phenomena which may occur in the system. You can look at those. Essentially, I told you the story. There are contradictory kind of requirements, and you have to analyze them all. And depending on what's going on, what type of thing is happening, you have to do things in a different way. Now, at the end of the day is that if you do snooping, you increase the traffic. If you want to have more parallelism and you want to have more cores, you increase the traffic. And you know, this is kind of funny. We say, you know, probably you are not stuck in traffic, but I am from time to time. You are part of the traffic, right? And this may sound like a bit of a contradiction, but it has a lot of message inside. If you are not there, you don't create pain for the others, you don't get pain for you. Then take the bike or take the train, if you can. But essentially, you cannot do that. Okay. Now, there is another implication here which we kind of discuss on when talking about caches. Remember the 3 C's? Capacity, compulsory, and conflict. Then we have the extra C, which is due to coherence. And why in uniprocessors the programmer may or may not have to deal with data layout and things like that. In a multiprocessor, the job of the programmer to deal with that is actually more important. If you don't make the data floor plan in a proper way, you will increase the conflict. The conflict misses, and it's not only as it is in a normal cache when if you have a miss, you go for the next. You have this overhead about, you know, updating and doing things in a proper way. Now, there are even some kind of, you know, strange things, because not all the conflicts are real. You have true sharing and false sharing. This is due to the fact that in a block you have more locations. Then a cache line, it's actually composed of a number of words. You are dealing with one location at a time, but you don't invalidate the location, you invalidate the cache line. Then if you have a situation like here, when you have forwards in the cache line, some of the sharing misses are correct, others are just artifacts of the fact that you have invalidated the location which is actually valid. Nobody damaged X2. It was okay, it was correct. I was working on the line and I changed X1, I write to X1, but because of that I'm invalidating the entire block. And then eventually when I have to look for X2, I will see, oh, but this is not valid. I have to bring it, but it is there. Now what can I do? What would you do? Maybe this will be my last question. Or maybe not. What would you do? Oh, you are very tired, sir. And bored. No. Then just tell me, what would you do? You don't know. Try to think.
Instead of
Let us try to think together. Where is my problem coming from? Did you understand what I was telling about, or you were just sleeping? Okay, then you cannot answer the question.
instead of
He was first.
instead of invalidating the whole cache line, I can go for the individual locations.
Yes, that's the way to deal with that, but will that not create a problem? The way I manage cache lines is I treat them as an entire. Yes? Then if I treat them as an entire, I should validate or invalidate them as an entire. If I do what you just said, it means that actually I am kind of changing the cache line dimension. Then I am going from a cache line with 4 elements to a cache line with maybe 2 elements in this case. And I'm invalidating the most significant part of the less significant part. You wanted to say something?
Yeah, maybe if you can, because only the true misses are actually the real problem. You could wait a little bit before broadcasting. You can take the false ones with you.
Yeah, but sure, but this will create even more uncertainty in the system. Then I think the only solution which could be applicable will be to split the cache line in smaller parts. But that will have an implication on the entire system. And then somehow it's a price that I have to pay. Or I may have to make more tags and some kind of other overhead which can have an implication on the cycle time. And you know, sometimes there are things which are necessary evils, you know? Yeah? Do you know the concept of the necessary evil? Yeah. Like going to the dentist? Okay. Now, when we look for the directory protocol, there is somebody in charge with the business. Then there is a player which is saying, you know, whether or not a block is in that or that place or things like that. Now, the first impression that I have is that you have a centralized control, and we all know that centralized control is bad, or not? Not always. Do you like centralized control? No? Who does like centralized control? It's like Putin, right? The supreme leader. No, from our point of view, it's not about democracy, it's about scaling, scalability. But this kind of centralized control, it's somehow distributed because you have a directory, but the directory, each node has a piece of this directory. Now, when you want to do transactions, the requesting, there is, you know, the process which wants to know about a copy, and it will send a request for information to the directory, and the directory will do the job. Then we'll take initiative to do this kind of synchronization. Conceptually speaking, it's similar, and it's treating things in different way, you know. It's again, essentially what I have is shared and unshared data, and modified and unmodified data. Whenever it's not shared, I modify it and it's my own business. Whenever it's shared, I have to be sure that a modification will be eventually visible to the rest of the people. And the way I'm doing it will have an implication on performance. And the way the system is treating those things will have an implication on the evolution of the program. Okay. You see, in a way, this kind of directory protocol, it's a message passing system. Then between the nodes and the directory protocol, there are different kind of requests. And you know, if you have a processor and you want to do something on a certain address, you send a message and things do happen, you know, the home directory will do things. Okay, I will not go into details on this. Now, somehow I can make a small summary here. We just took a very, very shallow look on this issue. It's just to give you an idea about that. There is a more advanced course in multiprocessors where you can learn, you know, deeper things about this. But somehow the technology was the one which decided that whatever we like, id est uniprocessors cannot go faster. That's not because we wanted to move to multiprocessors, we had no other choice. Now my question to you, and it's more a philosophical question and you don't have to answer that, is why do we want to run faster and more complex applications? And there is a follow-up question on that. How much of the functions of your smartphone are you actually really using? That's for you to think about that, okay? You may say, you know, I'm using all of that and I'm very happy with the evolution of technology, or you may say, I'm not sure if I really need those. But the people, they have to sell, right? I'm making business and I want to sell. And in order to make customers happy, I have to have more computation power. The uniprocessor is gone. I go for multiprocessor. Now, multiprocessor created a lot of troubles. And the paradigm that we know, which is nice and clean, even though not exactly like a mathematical formalism, did change. And implications are essentially on the memory. The rest of the workhorses, you know, they are given a job and they do it. You know, if you have a divider, the divider will do division. Or multiplication, it might be a programmable one. But that's it. The memory is the one which creates the problems. And then when you go for multiprocessors, the main issues are the interconnection, the memory management, and the way you map the application. And we kind of went fast into those. Now, memory coherence, it's also, memory consistency, it's also important. And in here, what we would like to look at, it's the way a processor can see the rights of the other processors. Why is that important? It's a collaborative work. Then I should be aware about the output of other processors. If I don't care for that, it's not collaboration, okay? Now, if I want to impose in here strict policy, I may end up in doing things in a serial fashion. And this is not what I want, because I want parallelism. And then for that reason, we relax a bit the condition on this kind of memory consistency. And I would like to enforce that order, but when it's too expensive, I relax a bit. The relaxation will have consequences on the result of the application. If the consequences are fundamental, I cannot do it. If the consequences are not fundamental, I will do it, and I have to be sure that I kind of keep things under control. And those are kept under control with some mechanism in hardware and with some libraries that you as a programmer of such a platform can make use of. Okay. Now you see, this is a simple example of consistency, and you have two processes, and depending on things are evolving, you may have different evolution of those programs. Now, if you follow the serial evolution, you should not be able to take the branches. Never, right? However, due to the way things are done in the memory system, you may be in processor 2, you arrive to the loop or to the branch, and then you know the update for A being 1 is not yet done, and then you can actually take the branch. And this is not deterministic, except if you impose some kind of restrictions. And those restrictions are, you know, like barriers, synchronization moments, things like that. You have to wait for, and you have those constructs in programming. Okay. Okay, now you see in here it's an example which is giving you some feeling about what will happen if you want to get consistency and the price is really big. And for that reason, we relax the consistencies. And we create what is called a data race. Okay? You are familiar with races from logic design, right? Okay, races relate to the strange evolution of a sequential machine which is getting into a state where it should not have been. You have hazards on signals. The same story happened here. Then you have data values which are not okay according to the evolution of the program. Then they will change the way your program will behave. And as a programmer, you have to prevent those if they are really problematic. Sometimes they are not. Okay? Taking that kind of guys, if you want to tell us how this is done, please take the lead. There are 4 more minutes. And then you may talk as long as you want. Okay? Now, if in the previous example, taking that branch will not have any fundamental implication, if you take it once, then you can take it. No point to do the effort to synchronize. If it is important, then you have to synchronize. And you know, there is what we call relaxed consistencies, and we can allow for different things to happen, not according to the rules. I mean, write must complete before read. That's normal, right? If I'm not completing the write and I'm reading something, I may read the wrong value. I may relax that, and that may have a kind of implication. And I may relax those, and then I may have a program which will never function, right? I should be aware of those because they can enable speed up if I'm using them in a proper way without damaging the logical structure of the program. And you see here a certain relaxation. You know, I have 2 processes, and if you relax the write, you may arrive in the situation when both ifs will be taken, even though they should not be. Okay? Now there is, okay, another example in here, the same kind of artifacts. And to enforce program ordering, I said that in the beginning, I said that also recently, you have constructs. And those constructs are essentially hardware level. And in here we have what is called link load and store conditional. And they create the possibility that you actually take for your private use a certain piece of memory. You load information from there, you write information then, and you guarantee that nobody is interfering with that. And what you do, it's called an atomic operation, which may be more complex than that, even though the name of atomic is wrong. When I say an atomic operation, the understanding is that this is an operation which will be not divisible. But this is coming from long time ago when people believed that the atom was, you know, the smallest particle and could not be split in parts. Then we should use a different kind of terminology. Then this kind of operation in atomic kind of structures is fundamental. And I think, okay, here there is an example of a program where you use that kind of things in order to be sure that you are doing an operation without interference. As you see, there are special instructions which you are given, LL and SC, then load link and store conditional. Then I am creating a load link, and if that location can be linked to me and is given to me, it will return this instruction a certain value, which is 0 or 1. Then I am trying to store there, and if the previous link was okay, I store there the location and I'm sure it was done. It may or may not be okay depending on what the others are doing with the memory. If it was not okay, then I could not link the location to me. I will return and I will try again. Then if I could not do it and the store failed, I will return to try, which is actually wrong label in the slide. Then I will try to do again, which is missing here, which is, I go here, here it should be tried. Then this is a swap of variables, what I'm doing in here. If you are a bit familiar with the instruction set, you can see that directly. And this, it's a construction which I cannot do if I don't have that support of those instructions. Then you see I have an instruction set architecture extension, which is special for the utilization of this processor in a multiprocessor environment. In a local, in a uniprocessor environment, those instructions are not needed. There is nothing I can do with them. Then what you see is that I'm changing the instruction set in order to support that. I have some libraries which are using that kind of instructions in order to manage the access to the memory in such a way that you get consistency, and then you as an application programmer, you use those. And I think my story is kind of over. I went through the material on the most important issues. Details, I didn't discuss them all. I tried to give you mostly the conceptual view on the most important aspects. Now, as I said, on multiprocessors, there is a course for that. On how you do the functional units, we have the computer arithmetic course, which is telling about those. About interconnects, it should be another course. I'm not sure if it is given this year about, you know, networks on chip and stuff like this. I'm pretty sure we used to have such a course, but I'm not sure if it is given this year. And for the other part, which is about programming, it's beyond my expertise. You know, I'm a hardware guy, but I'm not saying it's not important. It's very important, but it's beyond, my horizon somehow. Then I think that's it. Please, okay, I'm a polite guy, but when I say please, I don't mean please, right? It's just like a British way of speaking. Then send me the updates on the groups because this afternoon